We're going to start with just a very basic overview of light and energy, and then we're going to move more into electronic structure at a later lesson. Waves are simply the propagation of energy, which energy is defined as the capacity to do work through a given medium. And light happens to be a type of wave. Light has a wavelength, which means the distance between two successive points on the wave. Typically, we measure this from crest to crest, and this is measured in the SI units of meters. So anytime we use the speed of light equation, we always have to make sure our wavelength is in meters. The frequency of a wave is the number of cycles of the wave that occur per second. So if you have a shorter wavelength, more of these cycles are going to occur per second. I also have a simulation that's posted on Canvas that kind of goes through the motion of a wave and how waves, the wavelength is inversely proportional to the frequency. So if you'd like a visual to help you remember some of these concepts, you can pause the video and actually access this link on Canvas. Light is an electromagnetic wave, which means that it propagates energy through space as an oscillating electric and magnetic wave. So it has two components to it. It actually has an electric component and a magnetic component too. But it has a wavelength, it has a frequency, and the equation by which we describe the motion of light as a wave is the speed of light, c, which is a constant, is equal to wavelength times frequency. So the speed of light never changes. It doesn't matter what type of light you have, it always moves at exactly the same speed through a vacuum, 3 times 10 to the 8th meters per second. The wavelength and the frequency, however, can change, but as one changes, they're inversely proportional. So wavelength gets bigger, frequency gets smaller, and vice versa. You should know the general order with which types of light fall within the electromagnetic spectrum. So gamma rays are the shortest type of shortest wavelength, I should say, type of electromagnetic radiation. They're also the highest energy and highest frequency. And then as we go through the spectrum, X-rays are less energetic, UV light is less energetic. Then we hit the visible region, which ranges from 400 nanometers to 750 nanometers. So red light has a longer wavelength than purple light. And then we start to get to lower energy types of light, such as infrared, microwaves, and then finally radio frequency, which has the longest wavelength, but also the lowest frequency and lowest energy. Here are two problems to help you review using the speed of light equation. So I'm going to ask that you pause the video at this time and try these two. And both of these problems are designed to help you remember how to use the speed of light equation, which you learned in your previous chemistry course. For the first problem, we're given the wavelength in nanometers. So therefore, we want to make sure that we're working with that wavelength in meters. So the first thing that I did was I converted it straight into meters. The speed of light never changes, so we always have access to that. And then the frequency is what we're solving for. Frequency is equal to the speed of light divided by its wavelength. The speed of light is a constant in meters per second. Notice how I put the units in here, and the meters are going to divide out to give us 1, which is going to leave us with our proper units of 1 over seconds or inverse seconds. So our final frequency for this type of light should have been 4.688 times 10 to the 14th inverse seconds or hertz. Usually frequencies are very large quantities when it comes to electromagnetic radiation. For the second question, we had to make sure that we changed our frequency from megahertz into inverse seconds or hertz. So that's the first thing that I did. Then I substituted my quantities into this speed of light equation. I have my final answer, which is 2.899 meters. Radio waves are very long, and their wavelength typically resides within the meter range. That summarizes the basic properties of light using the speed of light equation, and then we'll be moving on to more advanced concepts with quantum theory in a later lesson.